This video is part of an online course on algebra and will be about groups. Before we begin, let me emphasize what we are going to achieve in the next few videos. Our aim is to, in some sense, have a deeper understanding of the common algebraic structures you have encountered in your school, namely the integers, the real numbers, the complex numbers and polynomials. Now, to do that, we will introduce one algebraic structure of the one algebraic structure after the other, each one successively building a bit by bit. So, the starting point is groups. Groups are probably the most ubiquitous and the simplest algebraic structure that is available to us. In this video, we will just introduce groups and basic properties. The study of group theory is a vast subject. So, in algebra 2, we will spend a considerable amount of time studying groups in more detail. So, with that said, let me introduce the definition. A group G is a set equipped with the single binary operation which we call star, and this star should be associative. There should be an identity element, that means there should be an element E such that AE equals AE equals A for every single element A in the set G, and every element should have an inverse, that is, given an element A, there should be an element A inverse such that A inverse is E. Now, each one of these terms, associative, has an identity element and every element has an inverse, we have studied in some detail in the previous video on binary operations. Let me give some examples. Note, the first example is somewhat fake because we have really not yet seen what the set of integers is, but as I have done previously and will continue to do so, I will use the set of integers as a model even though we have not yet studied it properly. We will study the set of integers in great detail in the coming weeks. But in any case, the set of integers with just addition. Note, there is another operation on the integers, multiplication, which we ignore for the time being. In the next video on rings, we will consider the set of integers with two operations, addition and multiplication, as a ring. Okay. So, the set of integers with addition is clearly a group. Addition is associative, there is an identity element, namely 0, every element has additive inverse, that is, the inverse of 2 is minus 2, for instance. The next example is the set of non-zero rational numbers with multiplication. Why non-zero? Because all of us know that division by 0 will result in a disastrous explosion. So, you cannot divide by 0, all other elements have an inverse, the inverse of the element A is 1 by A. The set of invertible n cross n matrices with matrix multiplication. For the latter half of algebra 1, that is this course, we will study this set of n cross n matrices, invertible ones specifically, in great detail. These are all examples of groups. I am sure that you have encountered all three before in your studies, and I am sure that you have the necessary tools required to check that indeed that they are groups. Now, let us introduce some notation. What we do is, technically a group, if you want to be 100% pedantic and non-lazy, you should technically write a group as G comma star as an ordered pair, because the set G itself is just a set, it is not an algebraic structure, there is no operation on it, it does not even make sense to say that G is associative, that makes no sense whatsoever. You need this operation to make sense of the group axiom. So, technically the group is a set G along with the binary operation, it is an ordered pair, but such pedantry is typically not engaged in a mathematics course. So, what we will do is, we will intentionally forget mentioning the binary operation. It is understood from context that there is a binary operation involved. So, we will just often say erroneously, but you should understand from context that there is no error, we will just say let G be a group. That really does not make sense, but it should make sense to you now. And as in a given situation, we will be considering only one binary operation, we will even omit mentioning the binary operation star. we simply write AB to mean the product of A and B using the binary operation star, which you should infer from the context what it is. Okay. So, we will engage in such shortcuts to reduce pains of notation, otherwise things will start to get really complicated notation wise. As it is, the mathematics involved is going to get pretty complicated, but quite interesting of course. We do not want to complicate it even further by introducing boring notation. So, as much as possible we will try to be very brief in notational matters. Okay. We should see some more examples. What better way than to start with just a set with one element. Now, I am going to make something, I am going to use this word, this word is very commonly used in mathematics, clear. Clear means this is too simple for me to explain, it's too simple, it's well beyond, I mean it's too low level for me to explain. That is what it means when I say it is clear, but here I am using the clear as a cop out. I will introduce the notion of homomorphism and isomorphism maybe 6-7 slides down the line. So, up until that this will not make sense to you, but let me anyway just anticipate what is about to come. I will say it is clear that there is only one group with one element. What is the meaning of only one group? That you have to wait patiently for the next few slides to understand. What I mean is, if you take a set just consisting of a single element, there is one and only one way to make it into a group. That is, introduce the binary operation star on this set, which does A star A equals A. This is the only possible binary operation on a set with one element, and clearly this is a group. Associativity is trivial, every existence of inverse is trivial, the identity element is forced to be A itself. So, if you are given a set with one element alone, you can make it into a group by declaring that element to be the identity element, and the binary operation is trivial, there is only one possibility for the binary operation, and that will give you the group structure. Now, what do I mean by it is clear that there is only one group? Well, if I were to take an element set with B, where A is not equal to B, there is only one way for me to make this into a group as well, and in some sense both these groups are exactly the same. The only difference is what we are calling that one element, whether you call it A or B, the binary operation is going to do the same thing, it is going to be the identity element. In some sense A and B are both E. So, we will make this precise when we come to isomorphisms, but for the time being you should have a sense of what I mean when I say that there is only one group with one element. Okay. The next most complicated thing is two elements. Let G be a group with two elements. Well, then one of them has to be the identity element, because a group can never be empty. A group must necessarily have the identity element. So, one of those elements I will call E, and the second one let me call B. Okay. Now, we need to determine what the multiplication table of this two element set is going to be, and that is not very difficult at all. Since every element has an inverse, the only possible way by which B can have an inverse is if B star B equal to E. That fully determines the multiplication table, because anyway B into E and E into B are both B itself, and B star B must be E. So, again when you have two elements and this two element set happens to be a group, one of them must be E, the other element must satisfy that it is its own inverse. And as you can see, if you take any other group with two elements, essentially it must be this group that we have just written down, except what we call E I could call something else there, what we call B we could call something else there. So, up to a renaming there is really only one group with two elements. Now, what about three elements? Things start to get slightly complicated, but a case by case analysis will still save the day. So, what I am going to do is I am going to call the elements E, A, B as usual, where E is the identity element. Now, let us think about what can happen to A. When you multiply A with itself, there are only three possibilities. Either you get back A, or you get B, or you get E. Now, suppose AA is equal to A. Then remember, we proved last time under no assumptions whatsoever that the identity element is unique. If I remember correctly, all you needed is associativity. The moment you have a binary operation that is associative and as an identity element, that identity element is unique. Maybe you do not even require associativity, let's just go and check back, maybe I am mistaken here. But under minimal hypothesis, you can do, you can check that you have cancellation, right. You also need inverses, of course, you also need inverses. Once you have inverses, and you require associativity and inverses. Once you have associativity and inverses, you have cancellation. So, this equation AA equal to A, I write it as AA equals AE and just cancel off the A's. So, I get A equal to E, which is not possible because I already have an E and the identity element is unique. So, we have now eliminated the possibility that AA equal to A. Now, what we do is look at AB, look at the product AB. Now, that product AB can neither be A nor can it be B by the same argument, by cancellation. You just write AB equal to AE, cancel, you get B equal to E, which is a problem. Similarly, AB equal to B, you cancel the B's, you get A equal to E, another problem. So, you cannot have AB equal to A or B. That means AB must be E, which in turn by uniqueness of inverses prevents the possibility that AA equals C. That is not possible because AB equals E, which leaves out the only possibility, that is AA equal to B. Now, here is an interesting thing. We have done our analysis on the element A. There is nothing special about the element A, which means whatever analysis we did for A works for B as well, which the net conclusion being that BB equal to A. You do not even need to prove that again in great detail because it is essentially exactly the same argument. There is nothing special about A that we have used. So, whatever argument we use to conclude that AA equal to B equally well applies to show that BB equals A. That means the net conclusion is we can describe this group as E A squared, where A squared is just a shortcut for AA. And this is called the cyclic group of order 3, which will become a very good friend of ours in algebra 2. So, this concludes the analysis of groups that comprise 1, 2 and 3 elements respectively. What about 4 elements? Well, I will just give one example of a 4 element group, and you can think about whether this is the only possible 4 element group or are there more possibilities for a 4 element group. Is this the only possible one? Well, this is called the Klein 4 group. Again, we will encounter this in some detail in algebra 2. It is denoted V4. It consists of 4 elements E, A, B, C, where E is the identity element, and here I have described to you the table, the group table, the binary description of the binary operation in some detail. Now, please check in painful detail that indeed identity element, inverses, associativity and all that, it is trivial. You can just spend 5 minutes staring at this table, you will be able to deduce that the Klein 4 group is indeed a group. Now, let me give a general way by which groups arise in mathematics. So, start with a set which is finite. There is nothing special about finite sets, but I am restricting myself to finite sets for simplicity. Denote by SA the set of all bijective maps from A to itself. That is, these are just functions f from A to A that are injective and surjective. So, functions from A to A which are injective as well as surjective. Denote this set by SA. On this set, we have a natural binary operation, that is composition of functions. Composition of two bijective functions is easily seen to be a bijection, and you have an identity element, namely the identity function from A to A, and inverse exists. If you have a bijective function f, the inverse is f inverse. The fact that composition of functions is associative follows very easily. Again, you should check this if you have not done so when you studied functions. Composition is associative. So, the set of all bijections from a set A to itself is indeed a group. Now, yeah, this is just I mean I have already explained all of this. This group has a fancy name, it is called the symmetric group on A, okay, and is denoted by SA. It is denoted by SA. If A equal to 1 to n, this special case, then instead of SA we just write Sn. Sn denotes the symmetry group on n letters. So, in a sense Sn describes all the ways by which you could permute around n elements. A bijection after all is just a permutation. You can think of the image of 1 as how you are permuting, okay. So, you can think of Sn as a collection of all permutations of the set 1 to n. Okay. The group S3, the symmetry group on 3 letters, you can describe this group as follows. Now, I have used what is called cycle notation, which I will explain in much greater detail in algebra 2, but for the time being you can just think of 1 2 as denoting that bijection that swaps 1 and 2 and leaves 3 untouched. This is a bijection from 1 2 3 to itself. So, 1 2 is just the shortcut for saying 1 goes to 2, 2 goes to 1, 3 goes to itself. Similarly, this 1 2 3 is a shortcut for 1 goes to 2, 2 goes to 3, 3 goes to 1, and 1 3 2 is a shortcut for 1 goes to 3, 3 goes to 2, 2 goes to 1. You can check that I have enumerated all possible bijections of 1 2 3 or all possible permutations. You can also think, you can I mean there is a more elaborate way to write down these permutations. For instance, this permutation 1 2 I can tediously write down as 1 2 3 2 and 3. Here what I mean is, below 1 is the image of 1, below 2 is the image of 2, below 3 is the image of 3. So, that you can compare that how concise this notation is as opposed to this, which is extremely long winded. So, we will stick to cycle notation. Now, what I am going to show you is the multiplication table on this group S3. Now, you should sit down and think, I mean, did I really work out every possible combination to get this multiplication table? Of course not, I used some sort of AI to do it for me, but you should think, is this table correct, or have I intentionally sprinkled some errors in this table? So, check and figure out, I mean this exercise is not entirely just to make you waste pen and paper, figure out how you could draw such a table. That is, how can you multiply 1 2 and 1 3 in a quick way. So, figure that out by yourself rather than me telling this. It is more interesting to figure it out yourself. Figure out how you could produce such a table without that much effort and without relying on a computer, of course. Okay. Now, let us come to the all important notion of subgroups. We will revisit all of these in algebra 2. This is just to give you a flavor so that we can proceed to study the integers, polynomials, matrices and all that, which are all examples of groups. Okay. A subgroup is nothing but a subset which is itself a group under the same binary operation. That is, you have a mother group and you have a smaller subset of that mother group. When you restrict the binary operation to that smaller set, which you can do, you end up with a group. In particular, that means the identity element should be there in the subgroup, every element in the subgroup should have an inverse, so on and so forth. As a simple example, the set of even integers is a subgroup of the integers with respect to addition. You can check this quite easily. And here is yet another way by which I can segue into the concept of isomorphism and homomorphism. You can technically treat Sn as a subgroup of Sn plus 1. How? Look at those permutations of Sn plus 1 which leave n plus 1 untouched. That is, function on n plus 1 2 3 4 dot 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 n plus 1 such that f of n plus 1 equals n plus 1. So, in this way you can think of Sn as sitting inside Sn plus 1, though technically this is not correct. Sn, an element of Sn is a function on 1 to n, it does not know what to do with f of n plus, it does not know what to do with n plus 1, f of n plus 1 is not defined. But we can think of Sn sitting on Sn plus 1 in a natural way. You can easily prove that the identity element of G is the identity element of H. That means any subgroup must contain the original identity. In a similar way, inverses are same as well. You cannot have an element A which is there in H whose inverse is not the same as A inverse coming from G. That cannot happen. Now, we come to the notion of an isomorphism, where I clarify what I mean by it is clear that there is only one group of order 1, that is one group with a which has only one element. How many groups of orders 1, 2 and 3 are there? Well, obviously the answer is infinitely many. Any set with one element can be made into a group by defining the binary operation to be the constant map. I mean, there is only one possibility, that is just it, A times A is just A, that is the only possibility. So, that means there are infinitely many groups which have exactly one element, but this is a bit silly. In an obvious sense, these groups are all the same. What I want to emphasize is, even though a group is a set equipped with the binary operation, the names of the elements are entirely irrelevant to the group structure. What is really important is how the elements interact with each other, and the way they interact with each other is via the binary operation. A rose by any other name smells just as sweet as one popular author has remarked. So, the names of elements are completely irrelevant. What matters is the binary operation. In other words, let us say I have a finite set and I have two multiplication tables. If after renaming the elements, the multiplication tables just look the same, then they are the same group. They are just the names of elements have just changed. So, that is formalized by this notion of a bijection. Let G and H be groups. An isomorphism from G to H is a bijection phi from G to H, such that for all A B in G, phi of A B is phi of A times phi of B. So, what I want to clarify is, notice that we have adopted this notation where we suppress the binary operation as much as possible. On the left, the binary operation is actually the binary operation in G, whereas on the right, the binary operation is the binary operation in H. Again, these have to be inferred from context. Of course, you can call the binary operation on G star, the binary operation on H hash, and write in tedious detail that phi of A star B is phi of A hash phi of B, phi of A hash phi of B. So, I am tripping up just by saying this because it is so verbose. So, you can understand that you save a lot of effort if you just suppress those things that can be easily inferred from context without any ambiguity. So, we will always suppress the binary operation whenever possible. So, what is this definition saying? This definition, you should think of the isomorphism as renaming, but an arbitrary renaming is not going to preserve the binary operation. This condition says, if you do the multiplication in G and then apply phi, or if you first do the multiplication, first do the renaming and then do the multiplication, both yield the same answer. Now, I think I have talked about the tree method before. It might be an appropriate time to pause the video, find the nearest tree, sit under the tree and think what this definition is saying. It is capturing the fact that if you write down the multiplication tables of G and H. This phi allows you to convert the multiplication table of G to the multiplication table of H. Do not press the space bar button up until you have really understood what isomorphisms really are, that you understand that it is a way to convert one multiplication table into the other. Okay. Since you are in this slide, I assume that you have pressed the space bar and you have actually sat under a tree and thought about this. Let us give a basic example of a isomorphism, an isomorphism. Now, groups in mathematics actually capture symmetry, and of course, I am going to say this for the 5th or 6th time, more about this in algebra 2, but here is a simple example. Take an equilateral triangle ABC. Okay. So, typically we draw equilateral triangle like this. Of course, my triangle is smaller than the true triangles on in the picture that are pre-drawn, but use your imagination, think that the triangle I have drawn is of the same size. Now, let A6 denote the set of all symmetries of the triangle. Now, you might ask me what is the symmetry of a triangle, and I am going to reply wait till algebra 2, but as a ad hoc definition, you can think of a symmetry as a map from R2 to R2 that preserves distances. That is, you map R2 to itself that does not distort distances. So, a symmetry of an equilateral triangle is a rigid motion of R2 that takes this triangle and maps it to itself. All those ways of transforming R2 to itself without distorting distances that leave the triangle fixed as a set. I am not saying the points of the triangle should not move, but it better move to a different point of the triangle. Best way is to see an example. If you take this triangle ABC and rotate it by 60 degrees clockwise, what will happen? A will move from here to here, and that is what has happened. And one second, I have drawn the triangle slightly incorrectly, it is my fault. So, I want A, B, C, yeah, okay. So, the convention for some weird reason in mathematics at advanced level is to always proceed counterclockwise. So, B must come after A and C must come after B. Okay. So, now when you rotate by 60 degrees counterclockwise, A will move here, B will move here and C will move here. Okay. And this is rotation by 60 degrees, this is the resultant triangle. Similarly, if you reflect with a mirror passing through the vertex C, what happens? Well, C, so again there is a slight issue. I have drawn the same picture, that is by error. So, let me just fix it now. If you reflect about a mirror, what you really get is A, B, C. Sorry about this mistake in the picture, it is unavoidable sometimes. Okay. You get this. Now, how do you think of this reflection? One way is to think that there is a physical mirror present passing through the vertex A and seeing what happens to the triangle. It is clearly the triangle will be fixed because it is a equilateral triangle. Another way is to think of this reflection by going to R3, that is 3 space. R2 is the plane, R3 is 3 space. What you do is you sort of do what you do when you flip around a dosa or something. You just hold this triangle and flip it on top of itself. That is how you view reflection if you have the flexibility of going to one dimension higher. Again, I emphasize this is just an example to sort of fix some intuition The details will follow in the next course. Okay. So, reflection and rotation are examples of symmetries of an equilateral triangle. Okay. Now, there are only 6 such symmetries. Of course, I cannot prove that now, I can prove it only in algebra 2, but there are only 6 such symmetries, and you can check that by composing this rotation and reflection, you can get exactly all these 6 symmetries. All 6 symmetries can be obtained by composing rotation by 60 degrees and reflection about the what do you say, the line passing through the vertex A perpendicular to the side BC. And now, when you draw the table for the group of symmetries, of course, this is going to be a group, you can check that. If you draw the multiplication group of these 6 symmetries, you will realize that up to a renaming, they are exactly S3, and you should work this out. It is going to be really interesting what happens. You are in for a surprise when you work this out. So, draw out the multiplication tables of this A6. This is called, by the way, this is called the dihedral group. I am calling it A6. So, please draw the multiplication table and compare it with the multiplication table for S3, and you will notice something surprising, that both are same. So, there is an isomorphism or between A6 and S3. Both are essentially just the same groups. Up to a renaming, both are just the same. Okay. Now, with that example done, we can move on to more general material, the notion of a homomorphism. You can think of an isomorphism as a perfect dictionary that allows you to translate between two groups. Whatever algebraic identity you prove in group 1 will be true in group 2, because the isomorphism respects the algebraic structure, the binary operation, and it is also bijective. But sometimes you might not get a perfect dictionary. That is, you might not be able to translate exactly, but you will still be able to respect the binary operation. This is the notion of a homomorphism. The definition is almost exactly the same as that of an isomorphism. The only difference is the following: G and H are groups. It is a homomorphism if the binary operation is respected, but phi need not be surjective, or phi need not be surjective or injective. That is, phi need not be bijective. It can happen that multiple elements of G get mapped to the same element of H, and some elements of H could be omitted also. So, an isomorphism is an homomorphism which is bijective, as you should check. Now, even though a homomorphism is not a perfect dictionary, it still preserves some basic algebraic features. What do I mean by that? Here and here alone, for convenience, I am going to denote the identity element on G by EG and the identity element on H by EH. What this says is, the homomorphism must necessarily take the identity element of G to the identity element of H. In a similar way, a homomorphism is going to take the inverse of an element in G to the inverse of phi of A. This is what you would expect from an isomorphism, because the multiplication tables are exactly the same. Identity must go to identity and inverses must go to inverses. This you will expect in an isomorphism. In fact, it is true in a homomorphism also. Just by the fact that phi respects the binary operation forces this. Let us see how. Well, all of these proofs smell the same. So, if you have smelt it once, you will never forget the smell, but let me anyway do it. So, phi of EG is phi of EG times phi of EG times EG, because identity into identity is just identity. Because phi respects the algebraic operation, this is just phi of EG times phi of EG. Now, multiplying by phi of EG inverse on the right, we get phi of EG equal to EH. So, what have I done? I get essentially what I have done is I have cancelled these two, but multiplying on the right means multiplying on the right of both sides of the equation. Just multiplying on one side is completely bogus. So, essentially I could have just said, just by cancelling off you get phi of Eg is equal to Eh. Notice that you get Eh because technically phi of Eg is phi of Eg times Eh equals phi of Eg times phi of Eg, and then I am doing the cancellation. Oh, I should technically cancel from the left. Let me do that correctly. Yes, I will get phi of Eg equal to Eh. Okay. The other part is equally boring and straightforward. What you do is, we have phi of A inverse times phi of A. Now, what the homomorphism property allows you to do is to essentially get rid of parenthesis, this parenthesis and this phi and this parenthesis. You get phi of A inverse A, that is because phi of AB is phi of A times phi of B, and A inverse A is just Eg. So, this is phi of Eg, that means this is Eh. Okay. So, we have phi of A inverse times phi of A equal to Eh. Now, multiplying by phi of A inverse to the right gives you phi of A inverse equals phi of A the whole inverse. So, these proofs are rather tedious, it is next to impossible to make them interesting, but they have to be done once. So, we are at a stage where we want to build a huge flying car and we have not yet invented the wheel. So, we have to do some legwork before we can get to the flying part. So, we have to bear with me for such boring proofs. Okay. Now, we come to something interesting. This is an algebraic concept that is going to come repeatedly in all three courses. So, the best way to learn such concepts is to keep revisiting them, each time adding layer over layer. So, we will see this notion of kernel at least 37 times in this course. May as well start right away. You have a homomorphism phi from G to H. You define the kernel of phi to be the set of those points that essentially get destroyed by phi, that is those points A that map to the identity element in H, phi of A equal to Eh. So, if you want to use more fancy notation, this is nothing but phi inverse of Eh. The pullback of the identity element in H under phi is called the kernel of phi. Now, the kernel of phi is a subgroup. Why is that? Well, what do we have to do to check that this is a subgroup? You have to check that if two elements A and B are in the kernel, then the product should also be in the kernel, because what is a subgroup after all? It is a subset such that under the binary operation of the original set, you should still get a group. If it so happens that if you take two elements A, B in kernel of phi and the product is not there in kernel of phi, there is absolutely no way by which kernel of phi can be a subgroup. So, first we have to check that the product is indeed there in the kernel, but this is triviality itself. Phi of AB is phi of A times phi of B, which is Eh. So, this shows that AB is in the kernel. So, at least there is some hope that kernel of phi is a subgroup. Now, what else must we show? Well, we must show that the inverse elements are also there in the kernel. But wait a second, should not we first show that the identity element is there in the kernel? Well, actually you do not need to, because if you could show that for any element A, the inverse is also there in the kernel, then we have already shown that the product is there in the kernel, therefore, the identity will automatically be there in the kernel. So, we are going to be fiendishly clever. What we are going to do is we are going to start by taking an element A in the kernel, then phi of A inverse is phi of A the whole inverse, because it is a homomorphism, which is Eh inverse, which is Eh. So, one second, I have made a slight error, let me just fix this. So, what we have is, there is no error, sorry. Phi of A inverse is phi of A the whole inverse, and phi of A is actually going to be EH because A is coming from the kernel. So, that is why this is EH inverse, which in turn equals EH because the inverse element of the identity is just itself. So, what we have really shown is phi of A inverse is EH, which means A inverse is there in the kernel. So, we have shown that whenever A is in the kernel, A inverse is in the kernel, therefore, E is also EG is also there in the kernel. So, what have we shown? Inverses exist and additive identity also is there in kernel, therefore, it is a subgroup. Wait a second, am I pulling a fast one on you? What about associativity? Well, the binary operation is the same. So, even if you restrict it to a subset, you never have to check associativity. Associativity is automatic even when you restrict the binary operation to a smaller set. So, the essence, if you follow this proof, you can extract a small lemma from this. Let me write down the lemma and see if you can prove it yourself. The small lemma you can extract is, if H is a subset of G, H is a subgroup if and only if whenever AB is in H, then A B inverse is also there in H and H is non-empty, So, if you have a subset, it is a subgroup if and only if whenever you have two elements AB in H, then AB inverse is also there in H, and of course, we need H not to be empty, otherwise it is going to be a silly case. Empty set can never be a group. Okay. So, please check this lemma. Now, the word kernel, I am sure all of you at some point of time or the other have heard of this word. It means core or essence. So, you have things like kernel of a nut. If you have a fruit, the kernel is supposed to be the nut inside the pit or whatever, I mean what it is called. There is also, in this context of operating systems, the kernel is the core that controls the hardware. It is the interface between the graphical interface or command line interface and the actual hardware. It is the one that does the communication with the peripherals attached. In fact, it controls even what is done on the CPU. So, kernel means core or essence. Now, we have called this funny set the kernel of phi. In what sense is it the kernel? Why is it the core or the essence? We need to understand why we are calling that the core of the homomorphism. Well, that is not so easy to, that is not so difficult to understand. Take an element G in H and let H be the image. Then a natural question to ask is, what are all the other elements in G that get mapped to the same H? In more fancy terminology, what is the pre-image of H under phi? Well, it turns out that knowing the kernel answers this question entirely. How? Well, the elements in phi inverse H are precisely the set of all elements of the form Gk, where k is in kernel of phi. So, if you know the kernel, you can figure out all the elements that get mapped to the same point as G, that is precisely Gk, where k comes from the kernel. Why is this? Well, suppose phi of G1 is H, take another element which gets mapped to the same element, then phi of G inverse G1 is phi G inverse, let me just, there is a slight typo here, phi G inverse phi G1. This is just because of the group property. I have applied another property of the group, phi of G inverse is phi of G the whole inverse. Okay. Now, phi of G1 is H, phi of G is also H. So, this is just H inverse H, which is EH, okay, which means if you take K to be G inverse G1, then that is an element of the kernel of phi, because we have just shown that phi of G inverse G1 is equal to EH, and therefore, we get G1 equal to GK, right, where K is G inverse G1. What about the other side? The other side is extremely obvious. If you take phi of Gk, then that is just phi of G times phi of K, which is H, because phi of K is just identity, it is just E. Okay. So, if you know the kernel, you can determine all the possible elements that get mapped to the same element H. So, in that sense, the kernel is the core of the homomorphism. So, this concludes this video about groups. We have been quite fast, but we do not need everything in this video to proceed with algebra 1. This is just to give you a taste and flavor. In the next video, we will introduce rings, and after that we will be in a position to study the integers. This concludes this video. This is a course on algebra, and you have just watched the video on groups.